Welcome in, everyone. We're going to get started with a new chapter today. We finished off last time talking about rotational motion and describing, how things may move, circular motion, things under a constant angular acceleration. All in all, it was very similar to that sort of linear case that we had, in chapter 2 and chapter 3. So we covered motion. Today we're going to introduce some more stuff about rotation. Specifically, we're going to talk about forces in sort of this rotating reference frame. Okay, so don't have my thing working yet today, so I'm going to write on the board today. We're going to start talking about torque. Torque is just a force that is describing something turning. Starting out in the semester, we described how things move, in a line, and then we started talking about forces, things that push things to get them to move. Torque is just a turning force. In fact, that's what I sum it up to be. So torque is a turning force. Let me put it up, let's see. I'll put it up over here so I don't have to erase it for later. So we have torque. The equation for torque is just force times lever arm. Torque is this sort of lowercase tau. It's this really fancy looking T. Like that, it's called tau. Torque is just a force times sort of a distance away from a pivot point. So in this case, let's call this, no, we'll call it R. Force times radius. That's not the whole equation, that's me sort of summing it up. I can also write torque as torque is force times the radius from where you're turning times sine of the angle. And I'll do a little demonstration. I'm going to keep that up the whole day. That'll be a bit more clear. So the very simple form, this form up here, force times radius, or a lever arm, is just describing how much something is being applied to turn, how much it's being forced to twist. That is torque. So let's see. That I have a little demonstration for torque. I need 2 volunteers. Who wants to try out something? Step right up. All right. Anyone else? Nothing bad's gonna happen. All right, let me actually, I'm going to move this back. That one's good. Up there, okay. So you guys are going to take these, and these are, I think they call them torque bars. You go like that. You're just going to hold them like this, like a bike, kind of like that.
Oh, like a bike.
Right, hold it straight out.
Touching?
You don't have to touch it. So, just like holding it out, how hard is it, to hold it that way?
Like this?
Yeah. Is it like too difficult to hold it that way?
No.
Not really.
Now, if it was to start rotating, it's going to go down like that, or this one, it's going to go down like that. Where's the axis of rotation for these two objects?
Piece of wood.
So it's this piece of wood. It's going this way. It's going towards you guys for both of them, right? It's going to rotate around this pivot point right here. This one's going to rotate around this pivot point right here. And so, when we're talking about turning forces, you guys put them down at the moment. As we're talking about turning forces, there are two ways to get a bigger torque, a bigger turning force. You could apply a bigger force, or you could increase the radius of whatever force you're applying. So put them out, straight out again, and they're not quite equal, but I'm going to put that one. I might need to get a different one for you. Same for you. Okay, you put them down. Be right back. So we have
How it worked out.
Awesome. Let's see if this will work. There we go. Now hold it there. Now hold it there. Is it more difficult?
Yeah.
There's more torque. There's a force right here. I'm going to hold it up for you. That's forcing it downward, and it's a specific radius away from the pivot point. Same thing for you. Yours is a little shorter. So force downward, radius, like that. So there's two ways, right? Like I was saying, there's two ways to increase the torque. You could add more force, so I could just add another mass. Harder?
Yeah.
Okay. Or I could take the same amount of force and increase the radius from the pivot point. Now both of you guys out again. That. What if I go that? What about right here? I don't know if anyone can do that. Yep. Okay. Yeah? A bit more? Okay, he can do it. Let's go one more. It's a lot more.
That's a lot.
It's the same amount of force, though. It's just at a different place. So we have this increase of torque just by where this thing is located. All right. That's all I need you guys for right now. All right. Maybe I could get one other person to come up. I have one more example torque. Yeah, come on.
I just have a question.
Yeah. What do you want?
So like, how would this be described as like, there's like a car, like a car has torque?
Yeah.
So is that like a similar torque, or is that like?
That's a similar torque, yeah. So it's how fast the force is being applied to the wheels.
Okay.
So in this case, I have one more demo if anyone wants to come up and try. So if not, I'll do it. You want to try it? Okay, say you're doing a project or something at home, and you need to twist something. You have a screwdriver, or maybe you have this big sort of like lug nut thing right here, and you need to loosen it. And you have a small wrench and a big wrench. All right, you think, oh, maybe I'll try the small one first. So this one, we're going to, let's see, put that on height. It'll actually grab. There we go. So try to like grab right here. See if you can loosen that. No? All right. Let's try the same thing, except this time we're just going to, you're going to try your hardest again, but you're going to increase the radius from where you're pushing. So try pushing on the very outside. So this big one. There, let's go on that. You got it. So increasing the distance from the turning point, from the pivot point, will give you a greater amount of turning force. And that's really, all there is to torque. Thank you. That's it. All right, give everyone like a round of applause. All right. Same things applied to like if you're doing house repair, you need to hammer some nails in. If you don't want to force a nail in too far, what do? You like choke up on the hammer. You go like up here. You're going to rotate. You're going to apply less force. Whereas if you want to apply a lot of force, you're going to make a large radius for a hammer. I don't have a nail to put it into that. So that is all there is to torque. It's a turning force. So I had two wrenches as an example up here. Let me kind of draw them. Okay. So that one right there, and I'll just do it one at a time. So this wrench, the one on the left, let's say we apply that torque we just saw. It was, in this case, a certain distance away from the pivot point. Okay. Certain distance away from the pivot point. So that would be right in the center of whatever you're turning. This would be like a nut or what was this one? This was the piece of wood for that first demo. Here, and let's say we apply a force. Let's say we push directly up right here. All right. We could measure the distance away from that pivot point. And that is that radius right there. I call it a radius is because if I keep going, it's just going to make a circle as it spins around and around. All right. This is, yeah.
So torque is happening to the nut?
Yeah. So it's right at the center right here. Okay. What if I didn't apply a force directly that way? What if instead I applied a force that way? Would the wrench turn at all?
No.
No. That's something like it's almost too easy to see if I have this on here and I force it that way, it's not going to make this thing turn. I'm just going to pull it like that. All right, well, I was going to do that on that one. Let's draw another one. What if I apply a really off-center angle? So like that. Do another. Wrench like that, okay. Let's say I apply a force at an angle. Now it's not so clear how much force I'm delivering to the wrench. This is where we're going to use that second, slightly more complex version of torque. Because torque is always a force that is tangent to the sort of circular motion. So we don't want this. We want to know how much force is being applied perpendicular. that much. So if I had, the angle, I could figure out, force that way. I want to know, I call it y, or I might call it like, I don't know. I'll call it y for right now. So I want to know how much perpendicular force to the wrench. And that's why we're going to use the sign, go like that, or, because if we have, let me put too many lines, like that, we have a 90-degree angle here. The sine of 90 degrees is just 1. And that means we're applying a maximum amount of force perpendicular to whatever we're trying to twist. All right. I put way too many lines on the picture. So pretty much we're only interested in this amount of force that is perpendicular, or I guess I could say tangent to the rotational motion. Yeah, I think that's correct. All right. That is that. Let me do this. Yeah. There you go. If you've seen this before, something that is, r sine theta, or something times something sine theta, that is just great. So from your math class, this is the cross product. That means that, since I am taking these two vectors, let me see, it's hard to do, we have this one vector, sort of this radial, position vector, and we have the force vector. Say we want to keep track of which direction the torque is going. And I don't need you to memorize this right at the moment. I just want to show it to you right now so it's not terrifying later. What this is saying is that I'm going to take these two vectors, I'm going to take my right hand, and we're going to first point out the distance away from the pivot point. So where is the pivot point? Where is the force being applied? And I point my hand in that direction. So I guess in the case of this example, here's that. Case of this example, the pivot point is in the center, and force is being applied here. So I point my hand that way. Then I curl my fingers. Curl my fingers in the direction of the force that's being applied. So is the force pointing up or pointing down? In this case, it's pointing up. So that, I have to curl my fingers up. And so that means we have torque pointing this way. It's my thumb's direction. And why we're doing this is because we need to keep track of whether or not we have a positive or negative torque. How much is this thing turning? How much force is this thing trying to twist with? So, sort of a brief, really rough intro to the right-hand rule. I'm going to get more to this next class. What we have, how it kind of relates to torque. And that's like a 3D picture. It's like distance, force. So torque is up, pointing up. All right. Sort of a simple example here. Force of 10 newtons being applied at 60 degrees. So that is pretty much that same problem I have over there. Let me draw it right here. I'm not blocking the word. Like that. Okay. Force is being applied. Let's say that angle right there. Let me make it better. 60 degrees. Okay? And that position is a specific distance away from the pivot point. That is the force. And I kind of just said we're going to use that slightly altered equation of torque. So we have torque is tau, force times radius, sine theta. What did I say, 10 newtons? 0.25 sine of 60. That is no. Let's see. All right. So we have torque is 2.16. What are the units? It's going to be newtons times meters, or newton meters. So pretty much what we're doing is we're finding this, that vertical component that we've always been doing. Call that like, sure. All right. Pretty straightforward. It's pretty much like, imagine trying to open a door at your house. You're going to push sort of perpendicular to the edge of the door. The doors are here. You're going to push perpendicular to it so you can apply the most force. If you push at an angle, the door is not going to turn that easily, right? If you push more and more in an angle, that's the case of me just trying to pull the door in one direction. I'm not going to make it twist. All right. Now, we need to take a brief, sort of a little aside, into defining the center of mass of some objects. So let's first ask ourselves why. Because now that things are rotating, there's a lot of different little particles in the real world, real life examples. A lot of the time, I don't want to describe the motion of every single little particle in something that rotates. And I have a picture of a ruler up there. So the ruler on the left, I was going to show you at, make a big rectangle. The ruler, or this desk, or this piece of aluminum here, it's all made of very small individual little particles. I was going to fill it up with dots. Show you that each of these dots will have its own motion, its own rotational motion. So maybe if I started rotating this meter stick right here, this 2 meter stick. So there's a little bit, there's particles right here that are going to spin around, and there's particles right here that are going to spin around. Imagine if I'm like, I don't want to have to do that. That's way too many. All of these things have their own motion. Instead, I want to be able to figure out one single point for any sort of solid object. And that is called the center of mass. So I pretty much take that object, I take the location of all these small little particles, and I say, that point right there pretty much describes how all of the mass is going to move. And I can say the whole mass of, say like this meter stick, you can condense it all to this single point right here. And eventually start balancing things, stuff like that. So, single point is the center of mass. Center of mass. So we just assume one single point has all of the mass of the object. So I guess I can say all of the mass. Is right there. Even though we know it's not, that just makes a lot of our problems way easier. So how do we actually take all of those little particles and figure out how we're going to, find that center mass? This is a lot. There's a lot of stuff that I have to account for. Let's start out small. Say I have 2 objects. Move that one up. Say I have 2 objects with 2 different masses. How do I find the center of mass between these 2? Imagine they're just like really abstract, just perfectly like spherical masses floating out in space. This is like the perfect, conceptual problem. I have one mass here, another mass there. I have no other sort of definitions for this. Let's say this mass right here, it's a lowercase m. This mass on the right is an uppercase M. So it just means it's more. All right, maybe we're going to be given a coordinate system, or maybe we have to make our own. Let's start our coordinate system. Let's start right here. Let's say that is the origin. That is 0. So right here. This is like a linear problem. All right. There and there, right there. Okay. So to find the center of mass of anything, this is going to be in one dimension. I'm just going to add up all of the single small little points. Mass 1, x1, the position. So just the mass times the position. And I can keep going and going and going as much as I want. Divided by the total mass. So okay, in the case of this problem, I have all the things I need except for, let's say this is, I don't know, we'll say that is, just making things up at this point. Let's call it 1 meter. Sure. So how do we find the center of mass? We just plug in what we have. We have m1 is a lowercase m. x1, that is 0. Plus m2, that's capital M. That is 1. Over m. Okay, very vague example I'm doing. All we have left is capital M all right, so that's sort of a ratio of this position. Let's say, keep this problem easy. Say that's 1. Say this is 2. That shows that we have a center of mass 2 over 3. And that would be meters, meters. 2/3 of a meter to the right. So that means we have the center of mass right about here. That makes sense. We have the large object over there, the small object on this side. The center of mass is not going to be directly in the middle. It's going to be leaning a bit more towards the more massive thing. Right? So that's kind of like this little demo I have right here. So pretty much a thing you could set up on your desk. It's a large wooden ball and a small steel ball. And the center mass is not in the middle. It's off to one side, towards the more massive object. So I have to go more towards one side. If I support it underneath the center mass, it will stay balanced. So that sort of represents this problem that I did right here. Okay, very general example. What if I have a bit more masses? What if I have, not two things, one big thing, one small thing, what if I have three things that are in a weird shape? This is where we are going to have to use what we know how to do in 2 dimensions. So we can find the center of mass in the x direction. So I'm using all x's here. We can find the center of mass in the y direction. So in this case, 1, 2, 3. I'm going to leave this room over here. Let's call this position right here, let's call that 0. That's the origin. And let's call this height right here y equals 0. So we're basically putting the origin right on this mass. Okay. Let's find the horizontal center mass. So horizontal. So same exact thing as I have over there. Except this time I have 3 objects to list. So let me label them. We have M1, M2, and M3. Let's say they're all the same this time. They're all the same mass. Okay. They're in different positions. So let's start out by saying M1 times its horizontal location, 1 plus M2, x2 plus M3, x3. I think the last thing, 1 plus 2 plus 3. I need to define what that distance is. So let's say this is 1 meter away in that direction. Let's say this is 1 meter away going up. Okay. The masses, I'm just going to call them M. All right, for 1 and 2 right here, it's 0. It's a horizontal position of 0. So we have mass 1, 0 meters. Whoop. Mass 2, mass 3 is the only one that has an actual value. That's 1 meter. Okay. Now it becomes, go like that. M1, M2 plus M3. Since I said they're all the same mass, they're all M, that means that is the same as this. So this is 3M on the bottom. That's 1M on the top. That is 1/3 meters in the horizontal direction. So I lost all my pens. So we have the center of mass, you need to go over a third. So it's kind of somewhere on that line. Now we need to find the vertical center of mass. Same exact thing. Except we do it vertical. So this time we have mass 2 and mass 3 that are at a height of 0 right here. So that means 2 and 3 are 0. Pretty much the same exact result. One-third. This one was 1/3 right here. So what that's showing us is that these three objects, they're just floating out in space. They go up a third. Right about here. So right here is the center of mass of these three objects. It is nowhere near any of the actual objects. So that is, I don't have any of the little toys I was going to show you. So that's showing that the center of mass of an object doesn't have to be on the object. So say even if they were connected by a thin little wire that connects all of them, that is not touching any of those wires. But that's the center of mass. If you were to support it right there, right at that point, you would hold all of the objects up. Okay. And this last one I wasn't going to do in full. I was going to just sort of summarize. Say we have all of these individual small little points. They're all the same exact mass. They're all spaced out the same. And we zoom out. That is what a solid object is made of. So we're just summing together all of those individual particles. That's how we get the center of mass generally being in the middle of some sort of uniform object, like this. Or if it's slightly skewed, more mass on one side, we're able to find it like this. It's sort of the same as like that wrench. Anyway. All right, now that we know how to sort of take an object, we could take maybe several points and find the center mass. Maybe even the center mass of an object is just given. It says it's this far away from one end, and it starts to rotate. Now we know that all of the mass, we can say, is right at that single point. Once we have this, once we know that where the object's center mass is, we can use it to find torque, or we can use it to apply another force to balance it. So I'm applying a force onto the center mass directly upward that's supporting it. Or maybe we have something like this bar. Center of mass is not in the middle. It is sort of right here. All right, so that means that I can condense this whole aluminum bar to, how much mass it is to this point right here. Like say, this bar has a center mass right here, so it's applying a force from right here. And pretty much use that for future problems. I will explain more if my tablet gets, if I get my tablet to work next time. But we can use center mass to create what is called a mechanical equilibrium. Otherwise known as a system in balance. I don't want to miss that. I'll erase this over here. There. So, the two conditions that we need for a mechanical equilibrium is that there's no external force being applied. So, net external force is 0. So the sum of all forces in all directions is 0. And that the net external torque is 0. So a sum of all torques is 0. Once you have that, you will have a system in mechanical equilibrium, or called something like balance. So like something like this. We have something over here. We have this little steel ball that is, if I ignore the wooden ball on this side, so ignore that, I have this steel ball. It is a certain radius away from the pivot point, my finger right here. So it's a radius away, gravity's trying to force it down, so that's a torque. It's trying to make it turn that way. But we have this other mass right here. Going from the center of mass, it's this radius away from the pivot point. So that radius. So that's a radius, and it's trying to force it down that way. So we have a torque trying to twist it that way. These two torques sum together to equal 0. And so we have this thing that is balancing. Other things that sort of are in balance just have all of the forces sort of in a line or twisting equal to 0. They sum to equal 0. So we've got some neat examples. I've seen like a video of someone like balancing a sewing table while someone was on it sewing. I thought that was, I couldn't get like a whole video on here. So, thought this was pretty cool. I can't do this. We have one of those, I'll bring out next time. I wish that was my dog. And I think that boulder up the top is from like a national park in Colorado. So that's right next to a road. Yeah, if you see the road, it's right underneath it. So things all like this are in mechanical equilibrium. There's no forces in any direction, or I should say, all of the forces are summing to 0. and all of the torques, all of the twisting forces, sum to 0. And I might do this sort of a trick right here. That's sort of like a really quick physics project you do in like high school. So that is kind of like the thing of me saying the center of mass of the object is not on the object itself. That's a spoon and a fork. They're just sort of stuck together. And the center of mass is right on that toothpick in the middle, and it's balancing on that glass. So I'm going to try to get the stuff to do that next time. If anyone has a dog that could do that, you could bring them in next time. All right, we're going to do one of these problems and might be good for the day. Let's see. I'll do it. I just wrote that. I'm going to put it over here. Okay, so we have a seesaw, sort of this playground seesaw that is in perfect mechanical equilibrium. On one side, on the left side, is a stack of bricks. The seesaw has sort of this little pivot thing in the middle. And there's a stack of bricks on the left side. It says that it is 0.5 meters from the pivot point. So we have a stack of bricks. Yeah, I have enough room. Bring it down a bit. We have this stack of bricks that is, we have a pivot point right in the middle. Call that R1. We call this stack of bricks M1. Let's put it over here. Okay. And we have two people on the other side that are making this a perfect mechanical equilibrium. One person is at 1.5. Call that R2. And another person is at R3. So let me fill out what all these are. This one was M2. This one was M3. We have M1. That's actually what we want to solve for. At the very end it says, what is the mass of the stack of bricks? So, question mark. You know the radius, the distance away from the pivot point. we do know all of the information about these two people on the right. So we know mass 2 is, what did I say? 70. And radius 2, 1.5. We know mass 3 is 50. Radius 3 is 2.5, right? Yeah. Okay. And we know that the system is in balance, in mechanical equilibrium. So that means that the torque trying to get this thing to turn that way, the torque trying to twist it that way is equal to the torque trying to get it to twist that way. And the way I can sort of, clearly label these is I'm going to say that one going to the left is counterclockwise, or CCW. Counterclockwise. And the one going to the right, I'm going to call clockwise, or just CW. Okay, so mechanical equilibrium. We have these two torques that are equal and opposite. We have so that's me just rewriting that. Now let's flesh out what each of those things mean. So there's only one object over here trying to make it twist this way. There are two objects in two different locations trying to make it twist that way. So for this first one, we have torque of that first object, mass 1, radius 1, is trying to make it twist that way. That's the only thing trying to get this to twist counterclockwise. What's trying to get it to twist clockwise is these two people. So we have the torque, we have to find the torque of the second person, torque of the third person. And I left it up right next to it. The equation for torque is how much force is applied. So we don't quite have a force yet. We need to multiply by something to get a force. Right, gravity. So we have, let's go like this. I'm going to write it all out so you can see that it will cancel. So we have force 1, radius 1 equal to force 2 plus radius 3. That. Next step is okay. So just sort of filled in all the spaces. And since every term has gravity in it, that's why I can cancel it out right now. If there was a term that didn't have gravity in it, I wouldn't be allowed to do this. So imagine I'm dividing everything by g. Then we have like that. M1 times R1. M2 times R2. How do we find the mass of 1? We get it by itself, one side of the equation. We just have to divide the radius over. Divide the whole other side by R1. So, all right. Let's see. So M2 70. Let's see. $70 times 1.5. I'll put it right here. $105. And that is 50 times 2.5. R1 was 0.5. M1 is 230 divided by 460 kilograms. All right. So having things in a mechanical equilibrium gives us another way of trying to solve for an unknown of some kind. And knowing that, we can say that things that make it want to turn one way, since I know it's going to be summing to 0 over there, that means everything that's trying to make it twist that way has to be equal to everything that's trying to make it twist that way around the pivot point. All right, I think that is all I want to do for today. All right, so I'll see you guys next time. I'm going to make the homework. I'm going to make homework, assign it tonight. You guys have till next Tuesday midnight